What if logging in did not require passwords at all? In this course, we'll connect blockchain basics, public key cryptography, wallets, and signatures into one practical identity story, so modern passwordless authentication feels understandable, useful, and buildable. We'll move step by step, starting with cryptographic foundations, then wallets and passwordless patterns, and then real Web3 login flows. From there, we'll cover authorization, security, privacy, and a capstone design you can apply. The course builds from foundations to application. Blockchain explains how shared records and transactions can create trust without one central owner. Web authentication brings in the practical need to identify users and control access. Cryptography connects the two, using keys and signatures to prove ownership. Wallet login then combines these pieces into a secure, passwordless flow. Choose the path that matches your experience and keep the learning active. If you're new, go step by step and review key terms often. If you have some background, move faster and focus on gaps like wallets, signatures, and authentication flows. If you're advanced, use the course as a reference. Whatever your level, pause, sketch ideas, run examples, and explain concepts in your own words. Before we get to wallets or passwordless login, we need the foundation. A blockchain is a shared ledger copied across many computers. Transactions are grouped into blocks, and each block is protected by a cryptographic hash. Those hashes link blocks together, so changes to old data become obvious. Consensus is how the network agrees which history is valid. These mechanics are what later allow identity systems to prove ownership without depending on one central database. Think of a ledger as a record book. Who did what, when, and what changed? In a traditional system, one central server holds the trusted copy. In a blockchain network, that record is copied across many participants. They help check new entries and agree on the shared history. Trust does not disappear. It is distributed across the network instead of concentrated in one owner. A block is like a sealed package of activity. Inside are the transactions users want recorded, such as transfers or updates. Around those transactions is metadata, a timestamp, a reference to the previous block, and other data the network uses to check order and validity. Once the network accepts the package, it is attached to the chain, and those transactions become part of the shared record. A hash acts like a digital fingerprint for a block's contents. The same data always creates the same fingerprint, but even a tiny edit creates a completely different one. Each new block stores the previous block's hash. If someone changes block 1, its hash changes, and block 2's stored reference no longer matches. That mismatch breaks the chain, making tampering visible instead of hidden. Blockchain records are not protected because files are impossible to edit. A copied database can always be changed locally. The protection comes from evidence. If one transaction changes, that block's hash changes, and every later link must be recalculated. Even if an attacker does that on one copy, other nodes still hold the original history. When copies are compared, the altered chain no longer matches, so the network rejects it. Blockchain is tamper-evident, not magically uneditable. Think of a transaction as a proposed change to the blockchain's shared reality. It might move tokens, mint an NFT, update a smart contract, or change an ownership record. The network checks whether the request follows its rules, valid signature, enough balance, correct contract logic, and so on. If the transaction is valid and included in a block, it becomes part of history, and the global state updates for everyone. When you send a blockchain transaction, it does not go straight into a block. First, a node receives it and performs quick rule checks. Is the signature valid? Is the format correct? And are the funds or conditions acceptable? If it passes, that node shares it with peers, who repeat the checks and spread it further. Invalid transactions stop traveling. This peer-to-peer filtering helps the network identify which transactions are ready for block inclusion. Consensus is how a blockchain turns many independent views into one shared history. Nodes may hear transactions in different orders, or some may propose conflicting blocks. The consensus mechanism applies network rules, incentives, and validation checks, so honest participants converge on the same accepted chain. Proof of work and proof of stake are different ways to do this. The key point is simple. No single boss decides. Agreement emerges from the network following the rules. Public and private blockchains solve different trust problems. A public chain like Ethereum is open by default. Anyone can usually read data, submit transactions, and, if they meet the rules, help validate. That openness supports transparency and broad participation, but provides less privacy. A private or permission chain limits access to approved organizations. That gives more control and confidentiality, but also requires stronger governance and trust in the operators. Now we can make the identity connection. A blockchain account is controlled by a private key, and a wallet helps the user use that key safely. When an app wants to authenticate someone, it can ask the wallet to sign a unique message. The app verifies the signature, confirms the account owner is present, and creates a session. No password needs to be stored, and the private key is never revealed. You now have your first blockchain mental model. Linked blocks preserve history, transactions propose state changes, and nodes validate, share, and agree on that history. You can also distinguish public and private chains by access and trust. Next, we'll connect this ledger layer to authentication, authorization, and access control.